All right, and this lesson is called Definite Integration with U-Substitution. Now, we have done U-Substitution before. That was the second lesson we did in this unit. But we are coming back around to doing it again with definite integration. So this time we're actually putting limits of integration on to our integral, excuse me, and then doing the U-Substitution. Now, there are two ways of doing this. I'm going to teach you guys the way that, number one, you have to know how to do it this way just because there are questions on the AP test that will set you up for U-Substitution, but then won't actually finish the U-Substitution problem. And so you have to know how to set it up in this way, but I'll explain both ways of doing it. So, first, let's just go back to talking about U-Substitution in general. Remember that our U would be the inside function. So in this case, our inside function is x squared plus 1. Therefore, du is equal to 2x dx. Notice that I don't need that extra 2, so I can get rid of it by moving it to the other side. That's 1/2 du is equal to x dx. If I start to do some highlighting on what's going to be replaced, the x squared plus 1 will be replaced with u. X dx will be replaced with 1/2 du. Now, here's where it goes two ways. It can either go the way of do the U-Substitution as you normally would, like we did in the second lesson. When you get back to the end of the problem, then you will, let's see if that can go away. I guess not. It's okay. Get back to the end of the problem and, excuse me, replace u back with what it equals again of x squared plus 1. And once you get to that point, then go back and do the definite integral by plugging in f of b minus f of a. That's one way of doing it, and it's perfectly fine, and you can get a correct answer, but what we're going to do is we're actually going to do what we call changing the limits of integration. So notice right now the limits of integration are from 0 to 2. I want to change those to be in terms of u's. So when x is equal to 0, u is equal to, and then we would just plug it in for what u equals, which is 0 squared plus 1. I'm plugging it in right... I'm plugging it in right here. So if I plug in 0 here, I get 0 squared plus 1, which is equal to 1. So instead of writing x equals 0, I'm going to write u equals 1 for my lower limit of integration. My upper limit of integration is x equals 2. So when x equals 2, u is equal to 2 squared plus 1, which is 4 plus 1, that's 5. So for my upper limit of integration, instead of writing x equals 2, I'm going to write u equals 5. Sorry, you might hear my dog in the background being crazy. So let's rewrite this in terms of u. Oh, now he's mad at me. He's growling. Hold on. Okay, he calmed down. So we're going to rewrite this in terms of u. My x dx is going to be replaced with 1/2 du, so that 1/2 is a constant. It can come out front. My x squared plus 1 is being replaced with u, so that's u squared. And then du. Now, this 0 down here, I guess I can pull out some more highlighting colors. This 0 down here is going to be replaced with a 1, and this 2 up here is going to be replaced with a 5. So wherever I see that 0 on the bottom limit of integration, I'm going to put a 1. So let me go do that now. And for the upper limit of integration, instead of writing a 2, I'm going to write it as a 5. So I'll write that up here now. Now everything is in terms of u. My function is in terms of u. The limit du is in terms of u. My limits of integration are in terms of u. I want everything like that to be in terms of u. The reason I say that I want you to do it this way is because, like I said, there are problems on the AP test where they'll say set up this U-Substitution but don't finish it. So the answer would look like this, where you have the integral from 1 to 5 of u squared du, and you have to know how to change the limits of integration in order to be in terms of u. So if I actually do this problem now, I get 1/2. The integral of u squared is u to the 3rd power over 3. Remember, I'm not going to do my plus c in this case because I'm going to just do my limits of integration to do the fundamental theorem of calculus from 1 to 5. This is 1/6 u cubed, and I'm going to evaluate the fundamental theorem of calculus from 1 to 5. So this is 1/6 times 5 cubed minus f of b minus f of a, 1/6 times 1 cubed. If I simplify that, 5 cubed is 125, so that's 125 over 6 minus 1 over 6, which is 124 over 6. And we could simplify it by 2. That would be 62 over 3. But I think that's about as far as that goes. So that would be my final answer. For our next example, we will set up our u again. So u is equal to, remember it's the inside function x squared plus 4. Du is equal to 2x dx. I don't need that 2, so 1/2 du is equal to x dx. If I start doing some highlighting to get rid of some things, x squared plus 4 will be substituted by u. X dx will be replaced by 1/2 du. And then if I change my limits of integration, if I say x is equal to 0, when u is equal to 0 squared plus 4, 0 squared plus 4 would be 4. When x is equal to radical 5, u is equal to, if I plug in the square root of 5 up there, I get the square root of 5 squared, which is 5, 5 plus 4, which is 9. So if I do this substitution, I have 1/2 times the integral from 4 to 9 of 1 over the square root of u du. And now my function is in terms of u, my limits are in terms of u, and my integral is in terms of u. If I actually perform this u substitution, remember that 1 over the square root of u is just u to the negative 1/2. So that would be u to the positive 1/2 if I perform the integral over 1/2. And then the limits are from 4 to 2. From 4 to 9. If I simplify this a little bit, I have 1/2 and that 2, it's going to be a 1. So this is just the square root of u from 4 to 9. So it's the square root of 9 minus the square root of 4, which is equal to 3 minus 2, which is equal to 1. Final answer. Again, you could have gone through the whole u substitution process if I would have never changed my limits of integration to 4 and 9, if I would have left them as 0 and radical 5. I could have gone through this whole process of actually integrating, and when I got to here, I could have changed this back to be the square root of x squared plus 4, and I could have used my original limits of 0 and radical 5, and I would have gotten the same answer. But I think it's actually easier, and you probably would make less mistakes if you changed the limits of integration. So we'll go ahead and continue doing it this way. All right, for example 4, I'm going to make u equal to 2x. Du is going to be equal to 2 dx. I don't need that 2, so I'm going to move it over. That's 1/2 du is equal to dx. Dx is going to be replaced with 1/2 du. 2x is going to be replaced with u. And then if I change my limits of integration, when x is equal to 0, u is equal to 0. When x is equal to pi over 4, u is equal to 2 times pi over 4, which is pi over 2. So if I do this substitution, I get 1/2 times the integral from 0 to pi over 2 of sine of u du. So the integral of sine is negative cosine. So this is negative 1/2 cosine of u from 0 to pi over 2. And if I do the fundamental theorem of calculus, this is negative 1/2 times cosine of pi over 2 minus cosine of 0. So that's negative 1/2 times cosine of pi over 2 is 0. Cosine of 0 is 1. So this is negative 1/2 times negative 1, which is a positive 1/2. All right, why don't you guys try and pause the video and work out example 5. I will also work it out and then unpause it so you guys can follow along and check the work once you're done. Pause it now. All right, so here's the work for this problem. Just to walk you through it really quickly to make sure you get it correctly. Cosine of x I chose to be my u, my inside function underneath the radical. The derivative of cosine is negative sine of x dx. I didn't need that negative, so I moved it over to the other side. So I was replacing sine of x dx with negative du, and I was replacing cosine of x with a u. Now I changed my limits of integration from x equals 0. I got cosine of 0 to be 1. And then if I plugged in pi over 2, x equals pi over 2, cosine of pi over 2 is 0. So my limits of integration changed from 1 to 0. Now, notice that this is technically backwards. I could have fixed it right now and done it from 0 to 1 and then changed this to be a positive and gotten the same answer. But when we're working with definite integrals, it actually doesn't affect our answer as much because you still do f of b minus f of a, the top number minus the bottom number. So it doesn't actually end up affecting your answer. But if you wanted to change it right now, or if you did change it right then, that's totally fine. U to the 1/2. The square root of u is u to the 1/2. So if I take the integral, that becomes u to the 3/2 over 3/2. If I plug in the 0 first, or actually I rewrote it a little bit first, and then I plugged in 0, and then I plugged in 1, so I got negative 2/3 times -1, which is a positive 2/3. So go ahead and fix any mistakes that you made, or let's move on and go to the next example. I think this is our last one. Yes, it is. Example number 6. All right, so on this one, I would be careful because it's not as obvious what u is and etc., etc. So I would actually split this up into two separate integrals around the addition sign. So we have the integral from 0 to pi over 6 of 1 dx plus the integral from 0 to pi over 6 of sine of x cosine of x dx. By doing that, I like doing it because now I think it's a little bit obvious that you're going to be working with this second expression to do a U-substitution. But the first expression actually doesn't need a U-substitution. So if I go ahead and actually do the first expression now, the integral from 0 to pi over 6 of 1 would be the integral of 1, which is x, evaluated from 0 to pi over 6. If I do the fundamental theorem of calculus, that would be plugging in pi over 6 minus 0, which is just pi over 6. So that's the very first piece of this. Then on this second piece, the one that I put a box around, we actually do have to do U substitution. So if I say U is equal to, and honestly in this case there isn't really one right or wrong because the derivative of sine is cosine and the derivative of cosine is negative sine. You could choose either one. I guess just to make it so that it's a little bit easier so you don't have to worry about the signs changing on you all the time, I'm going to make my U equal to sine of x. Therefore my du would be equal to cosine of x dx. If I do some highlighting, cosine of x dx is going to be substituted by du. And sine of x is going to be substituted by u. And if I change my limits of integration, I have that when x is equal to 0, u is equal to sine of 0, which is still 0. When x is equal to pi over 6, u is equal to sine of pi over 6. Sine of pi over 6 is 1/2. So if I do this u substitution, I get plus the integral of u du, and my limits of integration are from 0 to 1/2. The integral of u is u squared over 2, evaluated from 0 to 1/2. If I do the fundamental theorem of calculus, that would be 1/2 quantity squared over 2 minus 0 squared over 2. So far we're working with this answer right here. So I'm going to pick up where we left off with bringing both pieces back together again. So we had this pi over 6 from the integral we were doing over on this side, plus this. So 0 squared is 0, 0 over 2 is 0, so I just have to evaluate this piece. 1/2 squared is 1/4, so this is 1/4 over 2, which is the same thing as pi over 6 plus 1/4 times 1/2, which is pi over 6 plus 1/8. And I think it's okay to leave it like that. You could technically find a common denominator, add them together, but it's not going to help us much in the numerator, so might as well just leave it like that for right now. And that is the end of this video with U substitution and changing the limits of integration to make sure that they are in terms of U.